started. Okay, stipendium Hungaricum TDK Teams. To the Teams I uploaded a lot of things. I will return for this. I also upload this stuff to the youtube.com. It has no purpose right now, but last year in the Moodle I could not upload large files. The maximum size was 10 megabytes, so that's why I uploaded everything to YouTube. Now I just do it, I don't know why. Okay, you learn chemistry right now. What do you want to do after this? Perhaps I asked this yesterday, but do you have anything in your mind? Do you want to stay in Hungary? Do you want to go abroad?
I'm not sure. I said I'd like to do my master's here maybe.
Do you want to work in the industry or in the academy?
I'm not sure yet about that.
What about you?
I want to continue with my master's after the master's.
Here?
No, I want to continue in the US only if I have the chance to. Yes, and then I want to work in the pharmaceutical industry probably.
What scholarship?
Pharmaceutical industry.
Sorry, I didn't understand. I understand internship, but I didn't understand the first part of.
The pharmaceutical industry.
Aha.
Pharmacy.
Okay. You know that you can start PhD immediately. You do not need MSc if you go to the US or this. You know the system better than me.
No, I didn't know that.
Here, you for the PhD you need an MSc, and until the very last years, if you had an MSc, then you was considered as intellectual. The college was not so highly ranked and appreciated. But now everything changed, but doesn't matter. In UK, in US, Australia, you can start PhD after BSc. And to go to the US, you checked what you have to do for admission at the university. Perhaps you did the same for this university.
Yeah, I searched for scholarship opportunities, then I found ENKEMNA0302. That's what I did to get here. So probably I'll also do that for the US, maybe go online and then check some scholarship opportunities.
You will be American. You will be Hungarian in the US and then American everywhere. What do you want to do?
I'm targeting for after I finish this bachelor study, I'm targeting to work in the industry, specifically in skincare products.
What products?
Skincare.
Skincare. What is skincare?
Like shampoo, soap, maybe.
I understand.
Yes, that stuff, and maybe in that time also I want to study in my master's degree while I'm doing my work. But for the country, I'm not really sure yet where I want to go.
In Europe, in Germany, in Australia, in Finland, and perhaps in the Netherlands, but I'm not 100% sure, there is no titanium free. Germany and Austria are not so tolerant country. I have very bad experience. That's why I'm here. Actually, I worked and lived in Germany, and the outcome was quite horrible. Okay, because if you just want. I'm working on this class right now. So I ask you what to do. Well, what do you want to do? Because it has influenced what will you learn in the next weeks. Okay? Okay. I know you are intelligent, but I will tell you a few times the requirements of this subject. So, you will write 2 tests from the material of these practical courses. You can use everything during the test. You have to fulfill 41% for both tests. If you fail, you can correct. I give you dates when you can do. And you will take a written exam. 25% from one test, 25% from other test, half of the result of the exam, that will give 1 grade. Okay? That's like the elementary linear algebra. Bibliography. Last night I checked all bibliography that I uploaded, and unfortunately only the Hungarian bibliography was useful. The others were fragments. I didn't find exercises, so I will do exercises myself. But I find some very, very interesting point that I would like to share to you. Okay. Let's pray. Perhaps this will work. So last time, I mean yesterday and today, we are talking about vectors. There are a lot of things that we can do with vectors. Okay. You don't know this? Do you know this? Have you seen this note 2 years ago? It is unfortunately in Hungarian, but you will not need this. I need this. Just very, very quickly. So you have these vectors. Let's start here. You have this vector. And this vector. And also this vector. So let's do it. To do this, you just multiply all components. It's not bad actually. Perhaps I will have enough space. Oh,
I think for A it's a -2 on the last one. It's 1, 3, -2, I think. It's a
Wait. It's B. One. Oh, yes, that's minus, then that's plus. Thank you. Okay, and then okay, I hope it's okay. It is. Next one. No, this is the next one. The next one will be something else. go. So this is, I don't know, theta. Just the scalar. Okay, so the scalar product. If you have two vectors, then however, it could be A, not only errad free, but N, and B, then so the definition this is general for both. For the components, okay, if I write in this way, is it disturbing? Sorry, you are on third year, but is it okay using indexes and everything? Okay, because someone last semester asked me what is this sum.
Yeah. What is on the top of the sum? The 3?
It's n. Here it's free. It's free. Here it's n, because that's the general stuff. So you we are dealing 2 and 3 dimensions, but if you have n dimension, you also can use this. In programming, the arrays are called also vectors. Okay? This is okay. This is quite okay. Now, let's move and the B, this is excellent. Or I can, no, I cannot. The B is OA cross B. Okay, about this. I never could learn by heart the formula for the components. Actually, you know what's this. So you have a you have a B, and you have A cross B. And the length of this is and the components. So if you have then you can calculate the E cross B. The problem is that I could not memorize this, but it's not necessary. Usually I use the internet, but there is something else. There are some symbols. One is this Kronecker delta. You have seen Kronecker delta? You and you? No? You never? You have seen Kronecker delta? Kronecker delta. Have you ever seen this?
Yeah, Kronecker.
Kronecker.
Sorry.
How do you pronounce? You are the American, so tell me. How do you Kronecker?
Kronecker.
Kronecker.
I don't know.
Kronecker.
Maybe it's not right. I don't know. That's all.
Okay. Physicists who are calculating a lot of the tensors, typically guys in general relativity, using a special way of calculating. The special way is using indexes. It has different rules. I learned it, and it was a long time ago. One stuff is this Kronecker delta. There is something else that's useful. This Levi-Civita symbol. Do you know Levi-Civita? How do you pronounce Levi-Civita? It is here, Levi-Civita. I pronounce Levi-Civita.
Yeah, I don't know if I've seen that one.
You never see it,
I don't
but
know.
that's important. So actually, I do not need to write this again. It's a weird stuff. It's one if you have this type of permutation. One, two, you know permutation. You know permutation. You know permutation. So if the index is 1, 2, 3, 2, 3, 1, 3, 1, 2, then it's 1. It's minus if it's in opposite order, and if the indexes there are some equal, then it's 0. Why is it useful here? If you have many programs like me, then let's check this Levi-Civita. And for the first component, that's I, then A2 times B3, then A3 times B1, then A1 times B2 minus A3 times B2 minus A1 times B3, and then A2 times B1. Okay. And now Gross product. Oh, yes. Oh, I used wrong term all the time. Okay, let's check here. A2B, A3 minus A3B, A3B1, A1B3, A1B2, A2B1.
This is for the levies.
Yes. No, you check. Okay, I have memory programs. I never could learn the vectorial products in components. I always need to check it. For example, that's why you can use everything in the test, because I also can memorize everything. But you do not need. You have this Levi-Civita. I didn't write on the table. And then from the permutations, you can understand this. It has an extension. Hello, morning. You didn't miss so much. Do you know what is Kronecker data?
What do you have?
Kronecker. How do you pronounce? Kronecker data? Kronecker data? Levi-Civita symbol? Doesn't matter. Just sit down. It's okay. You didn't miss so much. After the class, if you want, we can talk about. I sent you a message. You read it. Okay, great. Okay, so this stuff, this Levi-Civita symbol, could be extended for four indexes or 100. I didn't check, but which is very, very interesting, that vectorial product, cross product, existing only in 3 and 7 dimensions. It's an interesting thing. We'll just write again. Oh, I cannot write, it's too small. Switch back. So this is a way to understand how it works. Okay, then. Oops. I just told the others I uploaded a lot of books, a lot of notes. The most of them is useless. We cannot use this. Oh, I didn't mention something. The director of your institute wrote me because I asked what to teach you, and he had some suggestion. Just it's English and 50 pages, so I have to go through. I need some time. One day is not enough. I don't find what I want to show you. It's not here. It's here. Okay, unfortunately it is in Hungarian. Do you know what are the complex numbers? Did you learn it from you learned it from calculus, didn't you? Okay. You never see. So the complex numbers could be also can deal in polar coordinate systems. You never. There is a complex number, one real and one it has an imaginary real part. One is the x, the other is the y axis. Have you seen this? And also it has a polar coordinate representation. You didn't learn anything about electrodynamics. No, you are not electrical engineers. No, okay, doesn't matter. This is for the, and I will look for something in English. This is how to deal calculations using just indexes without sum and product and anything. There are some rules how to do it. Here you can see the cross product, the vectorial product, for example, in three dimension. Actually, this is the same that we did. Also, you have the Levi-Civita symbol here. And the Kronecker delta. That you are not physicist, and the physicist guy is missing because you are all study chemistry. One male signed for this course, and he studies physics. Okay, doesn't matter. It's not so important that he is not here. Yeah. Okay, I don't know what to do with this. I can finish this. I can finish this stuff. Continue. Let's see. It's not the best actually. It's not really visible. Okay, I have this and. Okay, so it's always a problem. So I just did this example to explain you why is this Kronecker delta and Levi-Cheeta symbol are useful. You can see, excellent. Okay. There is something very interesting, this dyadic product. If you have two vectors, you can do this operation with components that you can see here. It has rules and everything, but I now cannot tell you anything about its usage. I mean in physics or chemistry, but it exists. And I find another product too, but it's not really important. Okay, coordinate systems. That will be fun. Next time I will talk about operators and matrices, and I can talk about special operators that I had no time. I had no time last time and last semester to talk about them. Okay, so you know the Cartesian, I talk about it. perfectly. Lost. So it's Z. It's okay. So I have described this last time yesterday. It's fading. The third one, okay. Different coordinate systems exist. You always use which is useful. And I told you about reference frame, but there is something else. The Cartesian coordinate system is good for parallel shifting and parallel transformations. If you need rotation, you prefer to use spherical coordinate systems. And there is a special coordinate system that's cylindric. This is special stuff. You have actually a polar coordinate system in the XY plane, but you have normal coordinates in Z. It is useful if you are dealing with something which is which has rotational symmetry, yes, cylindric or paraboloid or something spherical. Okay, so this is a direct application. This is my paper. It's under construction. What you can see is a special coordinate system. It's geocentric solar ecliptic. I will explain what is this. And there are two paraboloid, rotational paraboloid object on the screen. This is so-called montopause. This is a so-called Baushock. What you can see is in the Cartesian system projection of the orbit of so-called cluster spacecraft. It doesn't matter. So these curves, not segments, but limited length curves, are part of spacecraft orbit. This is in the XZ, this is in the YZ, and this is the XZ plane. But this doesn't help you so much. The Earth has a magnetic field. The upper atmosphere of the Sun is quite hot, and there are different processes, and it accelerates and becomes so-called solar wind. It also has a magnetic field. The full solar system is in hyperophanic, superophanic, supersonic, supermantosonic stream. Do you know what is supersonic stream? Have you ever seen, for example, I don't know, MiG-28 or an F-41?
The cone behind the, like,
Yes. So if the supersonic, if you are traveling very fast, then something, a special thing called shock forms. If something exploded, it also happens. Doesn't matter. So which is important? We have somewhere there the Sun. The solar wind comes. We have the poor Earth. And there should be an impact, but it's not really possible. So so-called Baushock forms, and then there is something in the Baushock. This solar wind is thermalization happens, and also its direction changes. And there is a surface where the kinetic pressure and the magnetic pressure of the solar wind and the magnetic pressure of the Earth is in balance. That's the montopause. This is the Baushock, and this is the montopause. What's the problem? The problem is it is in 3 dimensions. It's rotational. And if I have a protection for XZ, for example, XZ means from the ecliptic, I check the XY is from the ecliptic. And also you can see this YZ, so it does not help you. If you want to decide or check whether the spacecraft is beyond or after this line, you need this cylindrical protection. The cylindrical protection is very simple. The x do not change. Here I use the z, but doesn't matter. The x do not change, but you sacrifice the y and the z information, and instead of the y and the z, you have a distance from this axis, and then you can understand where is your spacecraft. Okay, sorry. This is the ball shock. If something is here, if you have a projection here, or if you have a projection here, it is difficult to decide whether you are inside or outside. So instead of this, you use a cylindrical protection, and then you don't have this. You just have this shape, and then also your hand, this point, is somewhere in this shape. So this is a special type of projection. Sometimes that's useful. This is a coordinate system. That is a coordinate system, and there is the Cartesian coordinate system. You have to transform something. Guess how do you do it? With matrices. That's next time. There are rotational matrices, rotational operators, projectors, lot of things that I could not tell you in last semester. Let's go back here. Okay, this is do you know how the solar system looks like? Really? Do you know what is ecliptic? Eclipse? No, eclipse. Ecliptic. What is ecliptic? That's the orbit plan of the planets. On the sky, where the planets are moving. The moon is a different orbit because it has an inclination. It's difficult to see anything. Doesn't matter, at least. Can you see at all this? Because it's not really visible, this green something. I don't know what to do when I take a pen from the secretary. The result is the same, like finding something here. I will keep this. So somewhere here is the okay. Geocentric solar ecliptic. The X is towards the sun. It's somewhere here. The middle is in the middle of the Earth. The Z is perpendicular to the plane of the Earth's orbit. So the Earth is so that's the ecliptic, and then you have a X, you have a Z, and the y gives this one. This is the geocentric solar ecliptic coordinate system. The mountospheric, this is what I use in my studies. The geocentric solar mountospheric is a system, but the x is parallel to this Earth magnetic dipole. You know the magnetic field. Earth has a magnetic field, and it's more or less dipole. And if you want to do something in the heliosphere, then you use this heliocentric Earth ecliptic. Okay, you are not astrophysicist, and you will never become an astrophysicist. I understand that, but you do this transformation with transformation matrices. 2 decades ago, there was a homepage. In the homepage, I downloaded the axes and the matrices and did the calculation manually or with the computer. There are much better possibilities for this right now. This is very, very difficult actually here. It's called SPICE. For example, you have a task. You want to plan a flyby at the Jovian system around the Jupiter. You know Jupiter? You know it moons? Io, Europe, Ganymedes, Callisto. For example, you want to see the Europe with the spacecraft. So the task is the following. Your camera is on the spacecraft. It should be turned to the Europe, and the spacecraft should be visible from the Earth. There is one coordinate system from the Earth to the Jovian system, other coordinate system in the Jovian system where the spacecraft is, and also the spacecraft has a coordinate system which is used and it says where the camera is looking. You can do this transformation. It needs hours. But if you use this SPICE kernel, you can calculate this. I once participated in a course at ESTEC in Netherlands, in Norway. It was 1 week only just how to use it. I still cannot use it, so I need help in this. Fortunately, this is the only possibility. CNRS. Do you know what is CNRS? You know NASA. You know European Space Agency. Yeah. Wait. NASA is okay for you. European Space Agency, no. Okay, doesn't matter. But CNRS is the French network of research. There are universities and there are research like here, but there are independent research institutes where usually the researchers do not teach, just do science. But this is mixed. In the post-Soviet countries, also in Hungary, the researchers were separated from the students and the universities. So the Wigner is in the mountains. The Eötvös University is at the Danube. The distance is 50 kilometers. I know because I cycled there, so I have measurements. This is physical distance, and you don't know where is the Wigner, but in the old days there were nothing, just forest there. So they put somewhere else. What is this? This CDPP. Okay, this is one institute of planetary research in Grenoble. Grenoble is a good place for skiing, also for hiking, but there is a very good research institute there. And this is their production, these traps. These traps, cannot. Okay, that's better. Not really. You have a vector. You coordinate, you transform from one system to other. For example, I showed this GSC, GSM, HE systems, or you know the Mercator system. You know Mercator? How do you pronounce Mercator? It's the latitude and longitude, but the pronunciation is not good. In all maps you have a Mercator system. How do you pronounce it?
I've never heard that name before.
How do you say this system? Geocentric system, or how do you?
I guess, yeah, geocentric.
Geocentric coordinate system.
It's a coordinate system, but you know Mercator. You know nah. My pronunciation is bad, so that's the problem. You must Mercator projection. You must know it. This is it, for example. This is a Mercator system. It keeps the angle, but the distance is different. You never heard about? Interesting. You also never? Okay, doesn't matter. So if you want to do the transformation, then you use these traps. But you learn about cylindric coordinate system, spherical coordinate system. You heard about it. Okay, then we can progress next time. Okay. So this. Okay, why is this important? You have one vector. You do the transformation. But for example, if you measure the magnetic field is also a vector. So you have a time series, a few million vectors, and you have to transform it. You cannot do it manually. You have to use a program code. That's a matrix transformation. That's the understanding. This is the usage of linear algebra. And without program, you can transform data from one coordinate system to the other. Do you understand what I want to show you or explain you? Okay, so this is an advanced applied linear algebra. I can give you very difficult problems in mathematics, or I can show you some practical stuff. Okay. Linearity. Linearity is really welcome everywhere because we can usually fix linear equations, and we do and find linear functions everywhere. Oh. Okay. Okay, these are spacecraft measurements. Actually, these are vectors. Actually, the first two rows are vectors. The first, this one, this are magnetic field. The components with the color lines, and here is velocity. All spacecraft had its own coordinate system, and everything was transformed for this heliospheric equatorial system. And then, after some analysis, we could produce first this, but which is nice, I want to show you. We could produce this one in 3 dimensions. So where are the spacecrafts? There are normal vectors. You remember normal vectors? And we assumed that the event is planar. And there were a lot of coordinate transformation with matrix and everything, actually with these straps. And we got a lot of normals, and we had a lot of positions also measured by vectors, and also those positions was transformed from one coordinate system to the other coordinate system. And finally, we got this, how the event looked like. The physics is not important, which is important the coordinate system, and also the this thing. Okay. I finishing this class, just one question. You remember the equation of lines and planes and everything? Do you remember? You remember because you just passed. Okay, doesn't matter. Perhaps that's also a good opportunity to do something. I don't know what you get from this, but I hope you will enjoy this class. Thank you very much, and see you next week. I will talk about matrices. A lot of matrices, operators. Do you know what is function? From calculus? Function, a function. Okay. 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 Thank you very much then. Thank you.